All right, gang, Math 6610. The purpose of this video is to demonstrate what we do when we have a violation of the sphericity assumption. Now, if I recall correctly, the first example, the only complete example I gave, we did not have a violation of sphericity. So life was good. We proceeded, did some I think we ended up with statistical significance. We conducted some pairwise analysis, post hocs as we call them, and life was good. No major bumps in the road. So I wanted to create an example and just kind of talk through, discuss what we do when this happens, right? When we violate the sphericity assumption. So the data set we have here is quite interesting, I think, because we're always interested, which professors are harder graders, right? So to test that, apparently under consideration for this study were professors A, B, C, and D, so 4 professors. Maybe Dr. Darbro, Dr. Whitaker, Dr. Blau, Dr. DeSario, whatever. And by the way, these are not the 4 of us, but. And then the values, this is the score that they gave. And if you see, there have been 8 different problems. So the within variation, the within sum of squares calculation here, as previously, which deal with subjects, this just deals with different problems. But you can see where the design of the repeated measures is appropriate. So for example, on the 6th problem, Professor B gave us 67%, whereas on the 6th problem, Professor A gave us 71%. And again, these are the same problems and obviously the same professors. Now, although it's tempting to just look at the means of the values across professors, I don't know what I did right here. That's not what I meant to do. What I meant to do was to look at this model, right? And although that's tempting, it's not correct. Why? Well, because we violate the independence assumption, and the traditional ANOVA command assumes independence. So I don't know what the p-value is for our study as we've designed it, but I know it's not 0.0108. Now, I want to investigate a little further, and I'm just going to look at the means across the professors. And when I eyeball this, I kind of think when controlling for the in-problem variation, I'm still kind of expecting to find that I have no statistically significant differences between Professor A, B, and C, but it looks like to me Professor D may be statistically significant there may be a difference in Professor D and Professor A, B, and C, but I don't know that yet. I just have to play out the process, or let the process play out, I should say. So I'm just very quickly going to go through some of the assumptions. So test of normality, we look at each one of these, greater than 0.05. So I can assume that the normality assumption is not a concern. Again, I would want to look at a QQ plot. If I was writing up the summary of this result, I would want to include a plot of the QQ plot. And switching gears to the equal variance assumption, p-value greater than 0.05, so we have no concern with normality or equal variance. Now, those 2 assumptions are specific to the ANOVA part. When we transition into the special type of ANOVA called repeated measures ANOVA, then we also have to test for sphericity. So that's what I'm doing here. I think the easiest way to do this is just to install the package or access the library EZ, and then use the EZ ANOVA command. All right, so warning there, it's converted problems to a factor, which is fine. We have tunnel vision. I mean, typically when we run something like this, we'll come to our ANOVA output, and we'll have tunnel vision on the p-value, but we don't here because we need to, first of all, determine if the Malkley's test for sphericity is statistically significant or not. In this case, this test is significant, which means that we have violated the sphericity assumption. Now, what do we do when we violate the sphericity assumption? All right, so when we violate the sphericity assumption, our focus turns to this epsilon. And epsilon is just the degree to which sphericity is present. If we have epsilon, and the bounds on epsilon are, let's just think about it for now, between 0 and 1. It's really not, but let's think about it between 0 and 1. It'll never be below 0, it'll never be above 1, but we can actually collapse it a little bit, but we'll talk about that in just a second. So we have this epsilon that's floating out there. Think of that kind of as a parameter value. Well, we can estimate it either using the greenhouse geyser, which is given as GGE, or the Hundt-Felt, which is, boy, I butchered that, which is the HFE. Now, under sphericity, and I'll show you in just a second, this is all about adjusting the degrees of freedom to calculate the p-values for the test. Again, don't want you to lose this, so I want this one to be tattooed to the brain. When sphericity is violated, that p-value is not stable. So we are attempting to find a more stable p-value based on these approximations of epsilon. So under sphericity, recall that the degrees of freedom for the numerator are just the number of measurements minus 1, and the degrees of freedom for the denominator are the number of measures in each measurement times the number of measurements minus 1. For this design, we have 4 measurements, so the degrees of freedom for the numerator will be equal to 3. Within each measurement, we have, 8, I believe? Yes. So we'll have 7 times 3. So the degrees of freedom here will be 21. Now, I think what follows is kind of cool. For the 2 correction methods, we alter the degrees of freedom. And we alter the degrees of freedom by taking each of the degrees of freedom times the estimated epsilon. Now, this estimated epsilon, again, is different for the 2 estimation methods. So, and I will tell you, there's a third comparison called the lower bound correction method, where this epsilon is just estimated by 1 over k minus 1. So in this case, it would be 0.33, well, 1/3. So the 3 epsilon estimates that we have for this problem is the greenhouse Geiger. Let's go back over here and pull that up. 0.5576. The Hundt-Felt, 0.712, and then the lower bound, which is 0.333. Just a parting bit of information. The lower bound is where we have the greatest threat, because it's of the 3 that we have here, it will always be the, well, no, I'm not going to say always. Yeah, I will say always. It will, because this serves as the lower bound for the greenhouse geyser. So this will always be the lowest bound, so it'll be the furthest from 1. So this is the greatest threat to sphericity. So you're kind of preparing for the worst case if you use that. Just an FYI, I don't recommend that approach. So now what we're going to do is we're going to recalculate the degrees of freedom. So for the GGE, we're going to take the 0.558 times each degree of freedom and get an adjusted degree of freedom for this estimate. For the HFE, we're going to take its estimate of epsilon times each degree of freedom, and we get another set of degrees of freedom. Under sphericity, we have the F statistic with degrees of freedom 3,21 is 3.7 with a p-value less than 0.05. When we adjust, when sphericity is violated, we have to choose one of these two. We do a new calculation based on the different degrees of freedom. This is for the GGE, this is for the HFE, and notice how the p-values have been adjusted. The F statistic doesn't change, but the p-values do because the degrees of freedom are changed. Now, do those numbers look familiar? Does the 0.0628 look familiar? Yeah, because it's given right there. Does the 0.0471 look familiar? Yeah, it's given right there. And we can see how these are calculated using a standard p-value calculation for the F distribution, 0.062 and 0.047. Now, your head's probably swimming right now with, let's see if I can get that a little bit clearer. What should you do? I guess when I say punt, pass, or run, with bowl season coming up, at least when I'm preparing these videos. Again, both of these are intended to estimate the epsilon. And I don't really know that there's a rule of thumb here. No, let me back up. I don't think there's an agreed upon rule of thumb. But the one that I typically go with is if both of my estimates, and let's throw out the lower bound estimate because I don't think I'd ever recommend using it. But if both are less than 0.75, I go with GGE. I would go with a p-value of 0.062. So are both less, so one estimate is 0.56. One estimate is 0.71, so in this case, both are less than the 0.75. So in this case, I would go with the greenhouse geyser. I would report the adjusted p-value at 0.063, so we do not have statistical significance. We did not reach statistical significance. If both are larger than 0.75, I kind of say toss a coin because it really doesn't make a lot of difference. The standard procedure, I guess, is to go with the Heimfeld. And in this case, I would report the adjusted p-value at 0.047. So we do have statistical significance. Now, you can play a little bit of an ethical reporting of stats here. Which one do you want? Do you want statistical significance? Well, report this one. If you don't, and let me back up a little bit. This is a unique example because we have one greater than 0.05, one less than 0.05. So I don't think I've ever seen that before. So I like this example because it gives us a choice. But I prefer a structure and just go with it and report the results and let the chips fall where they may. So in this case, if both are larger than 0.75, I would probably report the Heimfeld. I wish I knew how to say that first. Maybe that should be an extra credit question. How do you pronounce that? And obviously I could figure it out, but just use Google, right? So if one is below 0.75 and one is above 0.675, which is not the case here, but you can clearly see how this one could be above 0.75 and this be below 0.75. Some people, I think it was Stevens, who actually I think taught at University of Cincinnati, says that we should average the two. Other people say just use the greenhouse geyser because it is below 0.75. I would probably be more in favor of this approach than averaging, but I certainly couldn't couldn't fault the averaging too much. So specific to our example here, what should we do? Well, I think at this point we should probably, since the greenhouse geyser is below, I'm sorry, both of them are below 0.75. As I said previously, let's go with the greenhouse geyser and report the adjusted p-value at 0.063. Now, even though our model is, and this is even going to get wackier, even though our model is not statistically significant in the presence of the violation of sphericity, I would probably go ahead and still run a post hoc test on this. So I would, let's see, I did call this data, right? Yeah. So I would go data values, data independent, paired equal true, and Pete adjust method equal Bonferroni. And again, wacky stuff here. Our model is not statistically significant, again, because of the violation of the sphericity assumption, yet we have one pairwise comparison, Professor A with Professor B, which is statistically significant. Doesn't end up what we thought it would end up, or doesn't end up what I thought it would end up, because of controlling for the variation between the problems, or what we typically think of as the subjects. So it's a really cool example because it really makes you think outside the box. When you're conducting a repeated measures, you got, okay, this right here. You have to take this approach, put it on the back burner, forget about it temporarily because it just does not apply to the design of your study. All right, gang, that's all I got. That should end the repeated measures ANOVA lesson.